Okay, welcome back. So I'm gonna make the assumption that you don't remember everything from before spring break. Let's do a little review, then we'll get to what we're doing. Okay, we have the postulates of quantum mechanics. Okay, what were they? What was the first one? Yes.
There exists for any system a wave function called psi.
Okay,
Information that can be known about the system.
good. So there exists a psi. That's your wave function for any system. And it contains all the information. Psi contains all the information for the system. Now, this isn't part of the postulate, but it's the interpretation. What is the dominant interpretation for psi? Copenhagen interpretation, good. Which means, let's do one dimension, one particle.
The probability finding the particle between x and x plus 2x
Is,
one.
no,
So wait, what did it say?
you look at this quantity here, dx. Okay, what does this mean here? That means,
Magnitude.
yep, yeah, sure.
Oh, the probability of finding a particle between x and x plus dx.
Okay, good. And then this is the size, this guy squared it means, yeah, so what this means here, this is really the complex conjugate times psi here, dx. And this right here is, we show that this is real. And this is your probability of finding. Part between x and x plus dx. When you normalize this wave function, what do you have to do with that quantity? Do I have the probability of finding here and here and then here and then here and then here? If I add them all up,
We integrate from minus infinity to infinity.
what do you get?
One.
You have to get one. What do we call that condition?
Yeah.
Well, Well, this is a Copenhagen interpretation. That's called the normalization. So the normalization condition is this guy here. What would happen if I had two particles in 3 dimensions?
All you have
What would I have to do?
integrate dx and dy.
I have to integrate dx1, dy1, dz1, the xyz particles of the first position. And then you'd have the same thing then for the two. That makes sense? How many integrals would you have for two particles in 3 dimensions? That's 3, 6.
You also have to integrate over the time or not? No, not integrate.
That makes sense? Okay. Postulate 2.
The particle position, momentum, and energy are replaced with operators that act on psi.
Yes, so now we consider the classical quantities. No. X, Y, Z, Px, Py, Pz, and E are replaced with, and now I'm going to put a word in here because now we know what that word means. But when we had this postulate, we didn't. Now I can put in the word Hermitian operators. With the Hermitian operators, well, let's say with Hermitian operators. X hat, Y hat, Z hat, PX hat, PY hat, PZ hat, and E hat. Okay. Now, what are these operators? The X, Y, and Z are easy because they just become
X, Y, and Z.
X, Y, Z. Then PX and PY and PZ go to what? PX goes to?
Minus H at partial of x. Partial stretch to x.
So this PX hat is your minus I H bar partial with respect to X. With Y, you put in the Y, Z, you put in the Z. Energy is different. What does that go to?
I each bar respective time, like control stuff.
This goes to here. And these act on these operators. Act on psi. Okay. We have that word permission. What does permission mean now? This is not part of the postulate. This is math part. That word permission means what?
An operator that acts on side.
We have to use an equal sign. So if the operator O is permission, what does that mean? Yep.
The integral over all numbers,
Over all space.
the conjugate of F, function G, dx.
So O, something here. The operator,
Sorry, that-
permission operator, and that acts on G dx
Equal the
equals.
integral from minus infinity to infinity. Of the
Okay, this is driving me nuts. Fast off. Okay, if I were a spy and if you needed to get information out of me, if you captured me, all you would have to do is have some obnoxious noise and not have it stop. And I'll tell you anything you want to know. I'll tell you things you don't even want to know. I will make things up. Just make the noise stop. Just please make it stop. Okay. And this here
yeah,
times
GDX.
GDX. Okay, anything that satisfies that is the permission operator. And it turns out there are three properties for this. What are they?
Um,
The eigenvalues of permission operator are real.
Yeah, so there are three properties associated with permission operators. Okay. One, the eigenvalues are real. Two,
the eigenfunction of the Hermitian operator are orthogonal.
so the eigenfunctions of O are orthogonal. What does that mean?
It has something to do with the integral
There's an integral
from minus infinity to infinity.
over all space.
Of,
I think we're calling him phi, right?
yeah,
Yeah.
Okay, phi I star,
phi j,
phi j,
dx,
dx equals 0 if
not even j.
I does not equal j. Okay, well, these are the eigenfunctions, meaning this O acts on phi I, you get lambda I, phi I back. If O acts on phi j, you get lambda j, phi j back. One more property.
The eigenfunction of the permission operator form a basis.
The eigenfunctions form a basis. Okay. What does that mean?
That is the psi I are a bit off.
So
You
that,
can-
that might be true.
You can write it as a linear combination of.
Get rid of the pronoun. Yes, and if. Get rid of the if.
What?
Yeah, pronouns are bad in math and science. Get rid of the pronoun. You had it. Get rid of it.
The psi I is basis functions that can form any arbitrary function can be written as a linear combination of psi I.
Okay, so f is any arbitrary function. I can always write that as a linear combination of my phi i's. You know, this is someone I of ai phi I. This is an arbitrary function. Okay. And that's true for any Hermitian operator. What's going to happen when you take the quantum mechanics course, you're going to find out how this same thing is going to carry over to matrices. So you're going to have Hermitian matrices. For those of you in the math methods course, to be doing information matrices in the not so distant future. But it's basically there's kind of different ways of doing quantum. One is with differential operators. Another way is in terms of matrices. And so you basically, you take this and you translate it then to operators. I mean, in terms of information matrices. Okay, that makes sense? Next postulate. And again, this is not part of the postulate. This is just the fact of being a permission operator. Okay, we're up to 3. Okay, what happens in postulate 3?
If we have a very large,
No.
no. Okay.
Yes.
Schrodinger's equation.
Okay, so that was Schrodinger's equation, and that's how we're going to actually find psi. And so how do we, you want the Schrodinger equation for any system, what do I do?
Write the classical energy to replace quantities with operators.
So you write your E classical. What is your classical energy always given by? Kinetic plus your potential. Then you make this operator. So you make this as E hat. And then this goes to your T hat and plus your V hat like this. And then this acts on your side. And then when you solve that, that gives you the Schrodinger equation. So we did that. And lo and behold, we have. Let's write it down. So this right here, this is the kinetic energy operator acting on psi. And then what's your V psi here? And this equals your I H bar partial with respect to T psi. Okay. And this is your E hat acting on psi. And if you solve that, that'll then be the wave function. Force postulate.
Well, when
When a system is measured, the wave function collapses into one of the eigenfunctions of what's being measured.
Yeah, so when psi is measured, it collapses. Into one of the eigenfunctions. Of what is measured. What are you going to measure? The eigenvalue. The corresponding eigenvalue. Is measured. Okay, so what that means here, let's say, oh, I have O here and I have this guy here. Right? So O might be the energy, it might be linear momentum, angular momentum. It doesn't really matter. These are the eigenfunctions for this quantity. So say from an eigenfunction, it means I can write any wave function as a linear combination of this. Why can I do this again? Because it's always
I think so.
always a what kind of operator? Hermitian. What is one of the properties of a Hermitian operator? The eigenfunctions form a basis. So I can write the wave function like this. So when I measure this, we measure psi. And what does it do? It's going to collapse into one of these phi's. So maybe this collapses into the phi 7 state with lambda 7. So you're going to measure the lambda 7 value, but your system now is going to be in that phi 7. Okay. That's what that means. That makes sense? Again, that's a postulate. Yep.
You skirting the edge of being off the screen.
I am. I'm going into the phantom zone.
Or on the other side.
On the other zone. Where's the phantom zone start? It's right here. So here's the phantom zone. So jet. We did not. We don't want that. Okay. I have no kryptonite. You know. Okay, but I do have a marker. I can put it on the wall over. That'll teach them. Okay, so questions for that? The last postulate.
All the operator in quantum mechanics that correspond to physical quantities are permitted.
No, that's not one of the postulates.
All the operator.
No.
We have a large number of identically prepared psi systems. The average value of some measured operator is
Average value of this is gonna be,
integral from negative infinity to infinity of the complex conjugate of psi, the operator.
acting on psi x. And again, this is your expectation value. And what does that mean? That means if I have this system here, here's a psi, this is an identical system here, same psi. This is a large number of identical systems. If I measure this one, it collapses into some state. Let's say it collapses into phi 3 with some value lambda 3. I measure this one, it collapses into phi 13 with lambda 13. I measure this one over here, it goes into phi 4, lambda 4. If I add up all these eigenvalues and take the average of them, I'll get this one to be here. That's about postulate status. Okay,
We'll get the,
well,
we'll get the operator. If we,
so we're good. This might be the energy angular momentum. This is gonna be something we're gonna measure.
oh, okay.
And so we go and measure each of these ones here.
The,
By the previous postulate, these all collapse into one of the eigenfunctions, the eigenvalue. But I take the average of all the eigenvalues.
Yeah.
I'm gonna get some average value, some expectation value. Right. That expectation value is actually just given by this. Okay. They're all the postulates. So once you have that, if you accept them, okay, then you get everything else in quantum mechanics and falls out very rigorously. Okay, yes.
What is like the very large number of systems that
Usually, okay, when you do these things, what is the large number?
infinite?
It's infinite. Okay, turns out that's hard to do. Okay, this turns out easier. Okay, now in practice, you can easily do it. You'd have to have some, at some point let's say you could do this. What you do is you just keep on measuring systems until you see that this value not changing a whole lot, unless it was not really changing a whole lot. You're saying good enough. Okay. All right. That's what you have to do with a lot of things, because you can't go off to infinity. So you go out to some distance, especially computationally. If you don't see a lot of changes, you say good enough. And go on through. Okay. So we started doing some things here. We're all the postulates. When we have test 2, what do you think your chances are having to tell me what all the postulates are again?
100%.
I think it's probably up toward the, beyond 90% level. That's FYI. Because without this, you're not doing quantum mechanics. It's just, I don't know what you're doing, but you're not doing quantum mechanics.
It's really funny though, there was in that 10% that it didn't show up on the test.
Okay. Well, that's it for you. Ha, okay. You didn't have to know it. I don't think you have to worry about that. So, then one more thing. We said, what happens if V only depends on position? Okay, so we took the 1D case here like this. That psi is going to have to be a function of what?
X and T.
Of x and t. So we made an assumption here. What did we assume?
The psi is equal to 2 function.
The product of 2 functions and all of those two functions.
Psi of x and t of t.
Yeah, just dependent on a function of position itself, which I just called a non-fancy psi, times a function of time. And what did we do with this? Okay, so again, remember when I said the four most important math techniques? What did I say the four most important math techniques in physics are?
Multiply by one.
Multiplying by one in a clever fashion.
Add 0.
Add 0 in a clever fashion.
Their expansion.
Taylor expansion. And the last one is
Separation.
separation of variables, which is what this one is here. This is used everywhere. Okay. So what do we do with this?
You plug that in the 1D for linear
Yeah, we
equation.
took this and we put it back into here. So if I take this and put it into here, what can I do with that capital T here and why?
Get rid of, no,
I can pull out through the derivative. How come?
oh, because it's constant, so it's not
It
dependent.
doesn't depend on position. So if I take this side here, put it into here, that capital T I can pull out through this derivative. Because it doesn't depend on time, it doesn't depend on position. That gives me this. On this side here, when I take the psi and put it in here, what can I do with the psi? Pull it out because
It's not dependent.
it doesn't depend on time. So I can then write this as. And then what did we do?
Divided by side,
Which psi?
the fancy side.
You divided everything through by the fancy psi. Okay, so let's do this side here. This is IH bar. What happens is sides cancel. And we're left with this. Now over here, what happened? The T's cancel. Now this one, I'm left with this. Left of that. Now, what do you know about this left side? And what do you know about this right side?
Each might-
Oh.
This side only depends on T.
And the other on position.
This only depends. I lost my phantom zone marker here.
And that can be,
Now, what do you know about position and time? They are
equal if both of them are constant.
one more thing. That's all true. But one more thing. Time and position are what kind of variables?
Independent.
Independent variables. It doesn't matter what the x position is, doesn't matter what the time value is, they're independent of each other. So what's the only way I can have something that only depends on x? Something that always equals something that only depends on time when x and t are independent of each other.
They're constant.
Equal constant.
Yeah, they both have to equal basically a constant. So they both have to equal a constant. I think we just want to see.
Yep.
Which
But-
it's gonna get a new name.
In the process, didn't we like also define a thing called like the Hamilton?
The Hamiltonian.
Yeah,
Yes,
that's
we're gonna get that. So what this gives me here is that this actually splits my equation into two pieces. This, and we get this. Looked at this, we had another name for that. You take that little side to the other side. Here. And I could rewrite this as this minus h bar squared over 2m. Here. Psi, because this is all acting here, and this equals c psi. Which is actually remarkably hard to say. This side here, what do we call this? This is the what operator? This is our Hamiltonian.
Each of them.
We have here is H psi equaling C psi. What's the name of this equation? Eigenfunction, eigenvalue problem. Okay. We gave C another name.
The time in
Called it E. Why did we call it E?
The Hamiltonian is the kinetic energy plus the, or kinetic energy operator.
This
plus-
is your kinetic energy operator. This is your potential energy operator. Kinetic plus potential is your total energy, so we call this the Hamiltonian. And so this eigenvalue here is going to be just regular energy E.
Oh, constant.
Yep. And this right here, so this is our eigenvalue here. Okay. And this right here is called your time independent.
one being non-relativistic Schrödinger equation.
One dimension, non-relativistic. Sure. Take that course in computational physics, and I'll show you how to solve that for pretty much anything. Take the course in quantum mechanics, you'll learn how to solve it for the traditional problems. Okay. That makes sense? Then we solve this one here. I'm just going to give you the name of it. We solve the time equation as well. The time equation is this. So I put in my E back into here. I took over my T. We solved this. When we solved this, we ended up with this T equaling some constant. And so it's e to the minus I e T over H. Okay. And so if we multiply these two things together, we have with the psi here, which is this, is really just going to equal some psi e to the minus I e T over H bar. And what did we do with that constant? We folded it into the psi. And anything you could write like this, what did we call these wave functions?
Stationary state solutions.
These are called stationary state solutions.
Because they're not position dependent.
The probability is not. So what that means here is that if you look at this guy here, what did we show that equals? Right, that's going to be this. What happens if I take this and multiply by its complex conjugate? What do you get?
Like square. The magnitude.
And we have psi star e to the plus I e T H. That was this guy. And my buddy here is this. And then what do these terms do? Cancel each other. That gives you this. And this right here is time independent. Which is why it's called stationary state. There's no time dependence in there. Okay. One last thing. Then we start seeing what we can do with this. Sorry for the extended review. I just find that usually after spring break, if I don't, I have to end up doing it later on. It's just better to get people to speed immediately. Yeah. So one more thing. We wanted to solve the Schrödinger equation for a simple case. What did we want to solve it for? The case where the potential is
Constant.
a constant. So what is psi? If V equals the constant. I put this all in here like this. Okay, now we beat on this. So the E is a constant and the V is a constant. So I'm gonna take the V to the other side. I'm gonna write it like this.
The total energy,
What?
like the total energy minus the potential isn't just the kinetic.
Yes. Okay. And so I'm gonna multiply through by the reciprocal minus h bar squared over 2m, and this gives me this. And what do we know about this whole thing here?
What's the,
Constant. So let's take the case. If E is greater than V, what I'm going to do you want to do the other one first. The clock's against me in this room too. Let's do the other case. Let's do that case. We have to do them both, but this one I can get for. Okay. So what do we know about this term right here? E minus V. This is going to be
Kinetic
in this case,
constant.
it's going to be negative. So I have a negative and a negative. This whole constant here is in
Positive.
positive. So what I'm going to do is I'm going to distribute through the minus sign. I'm going to write it like this. And this right here is a positive constant. Okay, I'm going to define this to be theta squared. Some books will call this kappa squared. I'm not going to. Kappa looks too much like K. Kappa looks like this. The problem is we're going to have a K in a little bit. And to me, kappa and K, that's starting to become evil. When you have a kappa and a K in the same equation, you're supposed to distinguish them. I mean, I think that's a little on the evil side. So I think most authors will call it beta. Okay. So our equation is this. These individual pieces I'm doing are probably going to be a little incoherent until we get the whole, when you get the whole thing put together, it's all going to make sense. But this is one of these things where be patient till it's all kind of set up. Probably on Thursday or Friday, it'll all come together and you're going to go, oh, this is really cool. But you're going to have to kind of see all the pieces put together. So the question is, how do you solve this? So we classified this on Friday. So what did we classify this equation as being?
As the second order.
Second order. What determines the orderness of an equation?
Well, the partial derivative.
The highest derivative. So second order.
Homogeneous.
Homogeneous. Meaning it's safe to drink. It's been homogenized just like what determines whether something is homogeneous or not? All the terms contain the dependent variable. In this equation here, what are our variables? This one right here. Psi and x. Which is the dependent variable, which is the independent variable?
The independent variable is x.
X is your independent variable, and psi depends on x, so it is the dependent variable. So this is dependent.
That's useful.
And x. This is independent. Okay, so an equation is homogeneous if all the terms contain the dependent variable. Okay, this term has a psi, and this term has a psi, therefore it is therefore it's homogeneous. If I had this. Let's say that was my equation. Would that then be homogeneous? No, because this right here does not contain a psi. If I had this, then it would go back to being homogeneous again. Okay, one more word in here.
Linear.
Linear. Okay. What does linearity mean? You look at the dependent variable and any of its derivatives. And those terms should just be by themselves. You shouldn't have them raised to a power of products of them. You shouldn't have things like this. Okay, so this is a derivative, this is just side by itself, but this would be a product, this would be a nonlinear term. If I had something like this, that would be a nonlinear term. Okay. If I had something like this, what would that be? Why is this a linear term after all this is squared?
Is that the
That's the independent variable. So this is actually linear, nonlinear, nonlinear, something like this. Okay, that would be nonlinear. There would be nonlinear. Okay. To know more about this, my colleague, Dr. Kirtland, is teaching a course in nonlinear dynamics and chaos in the fall. And the course is going to be what happens when you have terms like this. What happens when you have terms like this, and like this. It turns out it all gets screwed up. And it's just everything falls apart. And then you start getting all this really, it's actually quite beautiful what you get. It's just the mess of it.
What course is that?
Okay. Well,
What course is that?
I don't know. I'm not certain which one it is. Okay. And what do we know about all the coefficients in front of the terms? What do we know about the coefficient in front of here and the coefficient in front of here?
They're constant.
They're constant. So the coefficients. In front of each term is constant. Okay, now here's the thing. Whenever you have a linear, homogeneous, differential equation with constant coefficients, you can assume, I'm going to prove this, you can assume a solution of the form. Okay. What can you assume the solution of a form of? E
To the px.
px, where p is a constant. What I want to do is show you why this works. Okay, the number of times you have to do this in life is absolutely phenomenal. The number of times you could say, well, this is so specific. This isn't going to occur a lot. No, this occurs absolutely everywhere. So this type of solution, it's really a sledgehammer. Door and mighty hammer. Okay, so this is just demolish the door. Okay.
I see it on my taxes.
Yes. Okay.
No.
Demolish everything. Just demolish. I demolish you. Whole basis of Ragnarok. Okay, what are we doing? We're gonna do a proof. Okay, so let's write a general nth order linear homogeneous differential equation with constant coefficients. How would I do that? So consider a general nth order linear homogeneous equation with constant coefficients. Good to know. Okay, so how would I write that?
Partial to the end.
Yeah, so I'd have basically an nth derivative. I'll call it y here. So that's an nth derivative. And it has the coefficient in front, which is a constant. I'm gonna call this an. So this an is a constant. Hey, if it's general, what else would it have next?
N plus one.
It's nth order.
Oh,
It's nth order.
minus one.
It has to be a minus because you have to go down, otherwise it'd be an n plus one.
Oh.
So this would be some constant. I'll call it n minus one. The n minus one y. The x n minus one with this, and I'm gonna go all the way down to my first derivative. And if it's general,
See,
well, then why can't I have a c? Then it would not be.
Linear. No, homogeneous.
It would not be homogeneous. Okay. It also won't be that. Okay. So this is gonna be a zero, just y. And this is gonna equal 0. Hey, but this term here doesn't have a y in it. How can that be homogeneous?
You can just move the a0y to the other side to make it homogeneous.
You could, but also y wouldn't matter.
0 times the standard variable.
Yeah, 0 times y is 0. So it's still homogeneous. Okay, so so let's say you're walking down the street one night and this equation accosts you. Don't panic, because it turns out that this equation actually has an Achilles heel. And it's this right here, e to the px. Okay. So let's do this. What happens if I take, so let's say we're gonna assume y equals e to the px. What's the first derivative of this?
P e
P
e
to
to the
e to the px. Really? Which is really p times y. Okay. What's the second derivative of this?
p squared y.
P squared e to the px, which is p squared y. What happens if I take the 13th derivative of this? What do I end up if I take the 13th derivative? P13 e to the px, which is just p13 y. Every time you take a derivative, all it does is put on a factor of p. Makes sense? So if we put this in here, something quite amazing happens. We substitute this in here, what do we get here? If I take the nth derivative of e to the px, what do I get?
p n
P to the n, e to the px, or just p to the n y. So this would give me an pn e to the px plus. Hey, what about the next term?
no 1 over pn.
You take the n minus 1 derivatives of e to the px, you get
pn minus 1.
p to the n minus 1. The next one would then be an minus 1, p to the n minus 1, e to the px. And I can go all the way down. My buddy here becomes
p e to the dx.
p e to the px. The last guy is just an a0 e to the px equals 0. Hey, what happens to all this?
The constants can be put together,
They're all different.
or the a and then.
You can factor it by e to the px.
Yeah, what can you do to the e to the px? I just cancel it.
Okay. Oh yeah, you can factor it and divide by yeah.
So what I'm left with is now this. So what is this equation called mathematically?
Oh, no. No. No? No.
It's just an nth order polynomial equation.
Okay.
This is just a nth order polynomial. Well, what did we start off with? We started off with an nth order differential equation. So what have we just done? We've converted our nth order differential equation to nothing but a nth order polynomial, which we can now solve for all the roots. Okay, so can easily be solved. The n roots. Okay, so if you solve this, you're going to get things like this. P1 will be a solution, P2 will be a solution, all the way up here to Pn. They'd be all the solutions to this polynomial. So what would I have? I'd have one solution, which would be e to the P1x. So that would be one solution of my differential equation. I could just as well put in this one here. And that gives me this one here. That would be another solution to my differential equation. And I could do that for each of these here. And so I could even have my last one here. So I've actually now easily solved my differential equation. Now, let's see how much you remember from differential equations. When you have a linear differential equation, if I have one solution, and if I have another solution, and another solution, and another solution, what can I do with them? What is also a solution?
Like adding them all together.
A linear combination. And that's only true with a linear equation. So when you have a linear equation, a linear combination of the individual solutions is also a solution. So the most general solution. Why most general? Is C1 e to the P1x plus C2 e to the P2x. All the way up here to Cn e to the Pnx, where C1, C2 are constants. Now, for 3 minutes, the reason why I picked this one here, we can easily solve now our Schrodinger equation. We have this. Apply. You are to the Schrodinger equation. We have this. How did we classify that?
Second order linear.
Second order linear homogeneous. What about the coefficients in front? They're constants. Hey, what kind of form of solution will we assume?
E to the px.
We're going to assume psi equals e to the px. Okay,
For p.
what happens if I take two derivatives of this?
Oh, we get the same thing, so we can solve for p. I mean,
Okay, well, tell me what happens when you take two derivatives of it.
you get b squared e to the
So you get to pulls on two factors of p,
beta squares phi.
beta squared e to the px.
Oh.
They go out. So why did we take that constant called beta squared?
It was
Why not just beta?
because p squared.
Because of this right here, because we knew what we wanted to get. This p squared equals beta squared. So p equals,
Potential minus energy minus potential squared.
p equals,
Beta.
Take that square.
Beta.
almost, what's the square root of 25?
Wait, what?
What's the square root of 25?
Five.
Plus or minus.
Plus or minus 5.
Oh,
We have two solutions here. We have a psi 1, which is e to the beta x, and we have a psi 2, e to the minus beta x. The most general psi in this case here would have to be what? A linear combination of these two individual solutions. What we have is this. That's your psi most general. Okay. Would be some constant C1 e to the beta x, C2 e to the minus beta x. So when your E is less than V, and V is a constant. And that's our very first side we have. There's a part of me when people walk by like that really slow. I just want to start saying like random things kind of loud just to see the effect. Like the voice in my head says that you should be dead, but I'm not going to listen to the voice in my head. You know, just see what they do. Okay, so let's do this.
Dr. Lounge, the principal's office.
Make sense? Okay. Why we want this to be obvious in a little bit. So what we're going to do next time, we're going to take this and make it
Bigger.
okay. E greater than B. We want to look at that, and then I want to show you what we can do with this. We're going to do actually our very first problem, which is going to become called the particle in a box. And I'll explain what that means. Initially, you hear particle in the box, and you go, huh? And we'll see what this means. But the amount of knowledge you can get from particle in a box is utterly phenomenal. Okay.
Cat and boxing.
Yeah, and you know, there you have it. Yeah. Okay. Have a good day.
You'll love it.
Yeah.
Oh, well. You know, stuff.